Okay, so today we want to look at modeling some different physical phenomena and how we can use exponential functions and logarithmic functions to do this. So if you have the agenda, there's a linked note sheet here that has these problems on it, but I went ahead and wrote them out here. So our first one, and we've been working on solving exponential equations. This is just an application of that. And really, it's nice to be able to solve them, but if they don't make any sense, and you can't see where they would ever be used, what's the point? So here, the number of bacteria in a culture is modeled by n of t equals 500 e to the 0.5 or 0.45 t, where t is measured in hours. So it's always important to figure out what t is measured in because, for bacteria, it's hours because they grow really fast, I guess. So we have 3 questions here. The first is just what is the initial number of bacteria? Now this is one you should be able to answer without a calculator because we know the initial number is what time? 0, right? Time 0. So that would be when t is 0. And that means that when you plug into here, your power, your exponent is going to be 0. Right? And we know that e to the 0 power is 1. So 1 times 500. So we might write this as that n of 0 equals 500. Right? Now, you could type it in your calculator. It would still give you 500. But just again, you don't need to. It's just going to be this multiple because, again, we know when time is 0, e to the 0 power is just going to give us 1. And then our second is how many bacteria are in the culture after 3 hours. So there, we're told 3 hours. That's going to go in for t. So this is just evaluating a function, just typing it in the calculators. The challenging part, so n of 3 would be 500 e to the 0.45 times 3. Again, just make sure that your 0.45 times 3 is in a parenthesis for the exponent. We calculate that out, and we get, I think I went ahead and rounded to the nearest whole number, 1,929. Is that what everybody had? Yep. All right, good. So there you go. And then the last one, we actually get to use some of our new solving skills to answer this last question here. So these are nice. It kind of shows you the function, how to kind of work with it. So after how many hours will the number of bacteria reach 10,000? So here, the hours, after how many hours? So this is our unknown. So t is our unknown in this case. It's kind of nice to know. Will the bacteria reach 10,000? So this would be our n of t, right? That's the number of bacteria after some unknown number of hours. So with this, we could just take our original model maybe and fill some things in. So 500 e 0.45 t. Well, we said t's are unknown, so it's going to remain t, but 10,000 will be n of t. That'll be the number we're looking for. So we'll get 10,000 equals 500 e to the 0.45 t. And in this case, it should look like the things we were solving over the last couple days. Right? We're going to isolate the exponential, so we'll divide both sides by 500. And we found that was 20, I think. Yeah, 20 e to the 0.45 t. Now at this point, we have a base of e. We need to get the exponent out of there, so we're going to take the natural log of both sides. And I'm not sure I mentioned it yesterday, but I almost always use natural logs when solving exponentials, and I figured out the reason why is that you can always tell a natural log what its base is instantly. Or if it's a common log or some other base, you have to look for that little number. It seems like more things I could goof up, so I like natural logs. So we'll take the natural log of each side, and here you should use natural log because we have a base of e. Right? Anything else is going to be a lot of extra work. So we do this, and now we get that the natural log of 20 equals 0.45 t. We'll go ahead and divide by 0.45. And again, don't you don't want to type anything in your calculator until this last step. It would be a bad idea to type the natural log of 20 in and get a decimal and then it would be annoying to have to rewrite it, plus you'd have to round it, right? Because this is going to be an irrational number. It's going to go on forever and never repeat. You can't write it other than just as natural log of 20. So we'll go ahead and do this division fact, and we get 6.66 hours would be the time, or maybe we'll write 6.7 hours would probably be plenty, close enough. It's probably a little bit too much accuracy, so let's say maybe 6.7 hours would be reasonable, which again does not mean 6 hours and 70 minutes. It means 6 hours and 42 minutes, I guess, 0.7 times 60. Any questions with that? So here we have our next example. In this one we have to write a little bit more of the model. So the fox population in a region has a growth rate of 8% per year. It is estimated that the population in 2000 was 18,000 foxes, I guess it's plural. Find a function that models the population t years after 2000. When you have real world applications, because of the way, when it's years especially, you'll see this idea a lot, t years after 2000. Because you wouldn't want to have to put, if you had to put the actual year in for t, you don't want to put a 2008 or, in for a variable that, or an exponent. That would not be good. So a lot of times you'll see this as whatever your initial measurement was, of 18,000, since that was in 2000, we know that's going to go here is our initial value. So therefore t will have to be the years since that initial value is kind of how that works. It looks a little different. So our model that we're given is that n of t is p sub 0 times r to the t power. And we didn't talk a ton about these models. I'm not going to hold you responsible for being able to find all these pieces, even though it's probably something you've done in the past. But anytime you're trying to find a growth rate, which is what r would be, it's just going to be 1 plus the annual change. So in this case, it's 1 plus 0.08 would be the growth. So the growth rate is 1.08. Okay. If you have a loss or a decay rate or a depreciation rate, like maybe you lose 10% a year, you'd say 1 minus 0.1 or 1 minus 0.08, and that would give you a growth rate less than 1. So again, a growth rate bigger than 1, it's exponential growth. The population is going to grow. If it's less than 1, it's going to decay. It's going to drop off. So we have r is 1.08. P sub 0 is 18,000. So for a, n of t is 18,000, 1.08 to the t power. Okay, would be our model. Okay, the next question here, we good on the model? It looked like most of you had that as I walked around. What is the population in 2008? Here, just make sure not to put 2008 in for t. It'll be ridiculous, right? That would be the year like 4008. It would be just foxes everywhere. Like the world, Earth would be covered like in 100 feet of foxes. It wouldn't be a good thing. So we want to do n of 8 is 18,000, 1.08 to the 8th. So that gives us approximately, well, I have 33,317. Does that look right to everybody? Now, and not to bring back memories of chemistry or anything, probably like 33,000 would be a better answer because this had 2 significant digits, right? I mean, if you're a scientist, you still have to deal with that stuff. Now, luckily in math, we can kind of ignore it, but if you're a fox scientist, I guess a zoologist, something, ecologist, something, you have to consider that. All right, so we have that number. And the last question is, when will the population reach 40,000? So this is very similar to what we saw in the last question with the bacteria. This would be n of t, correct? And in this case, t is our unknown. We don't know the number of years. That's what we're looking for. So, and now we're not going to guess and check. We're going to actually use our solving techniques to do this. So here we will get 40,000 equals 18,000, and then 1.08 to the t power. Now to do this, I'm going to have to isolate the base like we always do, right? That's always something that we do. So I'm going to go ahead and divide both sides by 18,000. Now I'm kind of lazy. I just typed 40,000 divided by 18,000 and then hit the fraction key on my calculator. Or I went to math 1 and hit fraction key, and it gave me 20 over 9. But again, it's going to give you some goofy decimal, probably repeating decimal. If it's ninths, don't use that. It's going to cause error in your final answer. We can very easily take a logarithm of 20 divided by 9. We just type it in our calculator. It gives us the answer. Here, a couple different options. Some people may want to do a base of 1.08, but I'm not going to do that because I don't have that on my calculator. So I'm going to go ahead and take the natural log of each side. Right, because once we've done that, on the left-hand side here, we have a t inside the natural log. Actually, I should probably put that there. I could go ahead and move that out front. So the natural log of 20 over 9 is t times the natural log of 1.08. So in order to solve for t, the natural log of 1.08 is just a number, right? It's just a number, just a constant. So I could go ahead and divide both sides by that. So we'll get the natural log of 20 over 9 divided by the natural log of 1.08 equals t. And just type that straight away in the calculator. Just as it's written, make sure that you close your parentheses around the argument of the logarithm and things like that. That's probably where I made a mistake before. And we get t is about 10.4 years. Now, you should always check that. So to check it, you'd want to go all the way back to our original equation and put in 10.4 and make sure that it's going to be close to 40,000. Okay, any questions with that? No. All right, good. Okay, so for our next model here, we want to talk about Newton's law of cooling. Right? It also has an exponential component to it. And now we can also have models with logarithms too. They basically just identify the pieces, plug them in, you're in good shape here. But, Newton's law of cooling tells us what it does is it considers the initial temperature of an object, the temperature of the surrounding area, and how long it takes it to cool down. Okay, so we have T of t equals T sub s plus D sub 0 and e to the negative kt power. There's a whole lot of letters going on there. So on your worksheet it has a little explanation here, but I kind of got the highlights here. With this, capital T indicates temperature, where little t indicates time in hours. So again, a lot of times in math, usually in math, uppercase and lowercase have different meanings. So T of t is the temperature at t hours, which is what we're looking for, or what we're measuring. T of s, T sub s, is the surrounding temperature, right? Obviously something cools down faster if it's in a freezer than it does if it's in an oven, right? That's why we have to consider that. D sub 0, this is the part that could be a little tricky for students. It's the initial difference between the object and the surroundings temperature, right? So throughout this whole model, the surroundings should be at a constant temperature. But if I have a boiling pot of water, it should be 212 degrees Fahrenheit to start with at sea level, and then it will, initial, did I spell it wrong? There, initial. But it should, it's going to decrease, but we'd find the difference between that. If it's 72 degrees and you had 212, you'd find the difference, and that would be D sub 0. K is up here is a positive constant based on the material. So what someone would do in a laboratory is look at a material, measure its temperature over time, and they could figure out what K is for different materials. And notice there's a negative up here in the exponent, which, as we would expect, that would indicate decay, correct? Because we're expecting the temperature of the object. It's the law of cooling, right? So it's cooling. That's why we still get to use E as a base, but then negative means that you could also think of the base as 1 over E. So let's see what we have here. So we have a bowl of soup in example 3, and they went ahead and gave us the formula here. They say the temperature at time after T hours is 65 plus 145 e to the negative 0.05 t. So, some questions we have are what's the initial temperature? Now, you could kind of reason this out based on the components, or you could just do T of 0. Either one would be fine. But we know this is the surroundings temperature, correct? And this is the difference between the soup and the surroundings. So that means the soup is 145 degrees hotter than the surroundings. Right, so that would tell us the initial temperature of the soup would be, is that 210 degrees? I added wrong on my paper. So you could reason it out, or you could just trust the function. If you do T of 0, you get 65 plus 145 e to the 0 power. And we know e to the 0 power is just 1. So that's going to give us 210 degrees Fahrenheit. So it is a hot bowl of soup near boiling. We good there? So, all right, temperature after 10 minutes. So that would be T of 10. Right, we're going to put a 10 in everywhere there's a small t. So 65 plus 145 e to the negative 0.05 times 10. Again, make sure to keep that, the whole negative 0.05 times 10 up there. And I went ahead and calculated that. Did anybody else calculate that? What did we get, 153? That's what I had. So T of 10 would be 153 degrees Fahrenheit. Okay, so the soup is cooled. The last part, just do this over here. It asks us, after how long will the temperature of the soup be 100 degrees Fahrenheit? Okay, so again, our model, we can copy this down and I'll move the board over some. 65 plus 145 e to the negative 0.05 t. So after how long, so since it's asking us about how long, that tells us that t, lowercase t, is going to be our unknown, right? So that's what we're going to be solving for. And then the other part is the temperature of the soup at some later time would be 100. So that would be right here. This would be T of t. So we get 100 equals 65 plus 145 e to the negative 0.05 t. So we need to solve that equation. Now, based on our previous work here, we know it's going to be more than 10 minutes, correct? Because at 10 minutes it was down to 153. We're looking for 100. So why don't you take a few minutes with your table mates there, go ahead and try to solve this equation, and we'll come back and see how that looks. Okay, to solve this equation, we have it set up as 100 equals 65 plus 145 e to the negative 0.05 t. So we're going to isolate. First, we're going to subtract 65 from each side. So 100 minus 65 is 35. And that's 145 e to the negative 0.05 t. True? And then we divide by 145. And that reduces to be 7 over 29 equals e to the negative 0.05 t, which is great. So then with this, to go ahead and solve this, since we have a base of e, we're going to take the natural log of both sides. So the natural log of 7 over 29, and we know the natural log of e, they just go away, correct? So we get, natural log e negative 0.05 t, come over here a little bit, and then from here, we're going to get the natural log of 7 over 29 equals negative 0.05 t. So now we're good to go. We're going to type this value in our calculator and then divide it by negative 0.05. So natural log 7 divided by 29 divided by negative 0.05. And that gives us 28.4 equals t. What is that in? That was about minutes of soup, right? So that'd be 28.4 minutes. Would be our answer there. Is that working for everybody? Yeah.